So now we're going to talk about Hess's law. Now, Hess's law basically says that if you can add standard state reactions, so remember 1 ATM, 298.15 K, together to get the delta H zero for reactions, or delta H naught, I should say, for reactions, you can do that without having to go and measure every single reaction separately, which means that this is very, very helpful when it comes to understanding what delta H is for each reaction. So you don't have to go to the lab and actually, run these things for hours and hours on end in order to get the delta H naught for a reaction. So I kind of consider this like a super fun game because basically all you're trying to do is add reactions together so that they equal what you're looking for. So here's the rules of the game. If you multiply an equation by a factor, you have to multiply all of it by a factor. This includes delta H. So like if you have H2 plus 1/2 O2 equals H2O, you would multiply all of that times 2 along with the delta H in order to add that. And basically you do this as you need to in order to get to your whatever it is that you're trying to look for. Okay, if you reverse the reaction direction, so in other words, you change the sign from going from reactants to products, and you basically take the reactants and the products and flip-flop them, then you have to change the sign of delta H. So in other words, if making something is a negative delta H, tearing it apart would be a positive delta H. Next, if a reaction is in a series of steps, delta H is the sum of all those steps. So basically, you just add things together at the end. That's what that says. And then I think it's an important note also that you only want the desired reaction in the end, and you can't have anything else left over. So again, that sort of helps you. So let's try a problem like this, because these are things that tend to give people issues. So here's an example. What is delta H naught for a reaction for the following reaction? And it gives you a reaction where 2BSO4 plus 2H2O yields PBS plus PbO2s and 2H2SO4. Whoa, that looks like a big reaction. I want to just point this out before we go further. Sometimes these things say delta naught, and in some other types of quizzes, exams, standardized tests, they don't put the little naught there. Don't let that confuse you, because those two things just basically say this is under a standard state. Some of them may not actually say that. So you look on a standardized chart in order to get the next bit of information. And so this may not be something that you're going to have at your disposal without looking at that chart, and that's okay. So please know that we, as chemists, know that, and we have these huge books that we can look this up in. And you've got to find the right reactions. That's probably the most challenging part in order to get what you need to get, in order to add these reactions together, because your goal is to finally, whatever you're adding together, you're trying to add it together to this plus whatever that delta H is for this reaction. So on a chart, I find that PBS and PbO2s and 2SO3 gives me 2 PbSO4. And I also find that SO3 is gas and this gives me this guy. And we have the delta H for both of those reactions. Well, so again, we're trying to add things together to get to where we need to up here. So because I've done this before, and it may take you longer to process this, and that's okay, I know that this first reaction here, we need to flip it backwards, because this PbSO4 that you're seeing here, that really was over here before I flipped that reaction, it's a reactant, it's not a product. And the numbers are the same because this says 2 and this says 2. So we just reverse this and take the products and reactants and flip them back and forth. So when we do that, we also have to reverse the sign here of delta H. But otherwise, we put everything else sort of like in the same situation that it would be otherwise. Then I need to look at the second reaction here. This second reaction, we have H2O and H2SO4, just like we see in up above. But notice that we have 2 H2O and 2 H2SO4 up here. Well, that tells me that I need to multiply the entire thing by 2. So you do that. And you put a 2 in front of everything. So remember, this is like, it's kind of like in math, you're trying to distribute that 2, which means that you also have to distribute it to your delta H of reaction. Now, if I was doing this by myself, I would probably line those two things up and add them together. But I was trying to show this to you in a step-by-step fashion. So all I did down here was I rewrote what it is that I had up above. Okay, so basically I'm just taking these numbers and pulling them down here. You use this arrow here as like an equal sign in math. And you add one side and you add the other side. But we also can see when we do things like this, these are the reactants and here are the products. In this case, we have 2SO3 going in as a reactant on this side. And even though it's in a different reaction, we have a 2SO3 coming out as a product. So they cancel out. This and this cancel out, and they're not even part of the entire reaction. So if we add this together, this is what we should get, which should match up perfectly with what you started off with, because that's what you're desiring to get. And when you add those two together and it gives you this, that tells you that you can add these two together and you can get this, because this number right here is what we were after, is that 504 kilojoules. I over-highlighted there way too many times. So if you need to, go back and start and see if you can do this just looking at the information that we have right here. So see if you can do that and try that problem on your own. Another similar type of reaction or type of math that we can use that's related to Hess's law, but it's not Hess's law, is that we can add the standard heats of formation for the products together and then subtract the standard heats of formation from the reactants from that. So basically, here's where that comes from. The amount of energy that it takes to make the products minus the amount of energy that it takes to make the reactants is basically how much leftover energy you have as you make those products. I hope that kind of makes sense. That takes a little bit to settle in sometimes. But essentially, if you add together all of the moles of the products and you multiply that by the amount of like their standard formation of each of those products, and then you subtract the reactants in the same way, you can get the delta H of reaction. This again takes a chart. Again, that is Appendix G in OpenStax. So here's what you might look at for a reaction. Let's take methanol as a combustion reaction here. So we have 4 CH3OH, we're adding it with 5 oxygen gas. That gives us 4 CO2 and 6 H2O. So you go and look up the standard heats of formation for all of those things. You find this information right here from that table that I'm talking about. And all you have to do now is use this equation, which is easier than it looks, to add these things together. So let's see. I've got 4 times the energy of CO2, because this is going to be a product. And so that's where this number comes from. This number right here comes from the fact that there's a 4 as a coefficient. And then we take the H2O, we find what that value is, and we say there's 6 of those. Minus all of the reactants, so that's why I put it in brackets, Our reactants are 4 of methanol, which is given right here. So I put that in down here. And that 4 again comes from the balanced equation. And then 5 of O2. Well, O2 is 0. So that makes things a lot easier. And then all you do is add and subtract this together as you would any other problem, and you get the delta H of that reaction. Those are really easy problems. A lot of this is gotten from your charts, so make sure you're reading those properly. You do need to make sure that you have liquid, gas, solids properly identified when you pull that off a chart, because you may have all 3 as options, and each of them have different heats of formation. So those are things to watch out for. Thank you very much. I hope that helps.